Well, hello. Today going to be talking about simple waves. Objectives. We're going to learn about the basic fundamental components of a wave. We're going to learn about the vocabulary for identifying the components of a wave, how to calculate the frequency of a wave, how to calculate the period of a wave, and how period and frequency are related to each other. All right, some good vibrations here. Simple harmonic motion. Examples of simple harmonic motion are as a guitar string, trampolines, things that repeat. A rubber band, if you take and pluck a rubber band, it vibrates back and forth, it repeats itself. So anything that could be repeated, you can take a spring and if you hang a mass from it and pull it down, it's going to oscillate up and down. It's going to repeat itself. That's going to have simple harmonic motion. The waves of a pool, the waves on a lake, those are simple harmonic motion. All great examples of simple harmonic motion. Period. That's going to be the time it takes for the motion to complete one full cycle. So, let's say I have 2 points here. And this right here, and maybe this over here is a pier. And we've got this water wave. Well, the period, T, is the time it takes to get from one complete full cycle. So, if a person were sitting up here on this pier, and they had a stopwatch, and the top of a wave hit the pier, the period, T, capital T, would be the time it takes to get to the next top of the wave. How long would it take, capital T here, for this wave to get over here to the top of this pier? That's one full cycle. Or if we had say a mass hanging from a spring, how long would it take for that spring to go down, for it to go all the way down and then back up to its original position here? How long would that take? That's the period. Amplitude. Well, here I say it's the greatest distance the shadow moves from its central position. Forget about the shadow. All right. And it's the wave. All right. So back to my example up here. This right here is what we call the middle of the wave, or it's called resting position. And maybe it's the waves here are 5 inches tall. Well, that right there is the amplitude. Down here, the amplitude, let's say that the spring, this K constant's really small. Let's say it goes down 10 centimeters. All right, that's the amplitude. That's how far it is from resting position. All right, and that's here we're saying central, and I use the term resting position there quite often. All right, cycle. All right, cycle is another word for a period. All right, this just another term for period, and I say that right down here. It's called a period. A cycle is a complete swing to and fro. So if we had a pendulum, all right, it swings to, it swings, and then it comes all the way back, and then it goes back to where it started. That is one cycle. All right, as it swings and comes back to its resting position, right here being its resting position. So that could also be called a cycle or a period. Notice they're used interchangeably. Frequency. Frequency now is the number of cycles in some unit of time. And I've given you an equation down here. Frequency, we use a lowercase f for frequency. I know it's another f. Frequency equals 1 over t. It's the inverse of period. The units, because this is, if we look at here, it'd be 1 over seconds, or we could say inverse seconds. Well, we don't like to say that it's 30 inverse seconds, so typically what we'll do is change this inverse seconds to hertz. So we would say one cycle per 30 seconds, because the frequency is 1 over the period. The period in this case meaning for one cycle in 30 seconds its frequency is 1/30th or 0.33 hertz. Let's say I'm sitting on a dock and the cycle or the period, one wave comes by every 2 seconds. So we could say that the period is 2 seconds. Well, the frequency then would be 1 over 2 or zero point 0.5 hertz, half a hertz. Now, quite often, right, in our notes, I've got an example here for you now. I'm going to have two problems here for you. Over here, I'm telling you that the period equals 0.2 seconds. I want you to find the frequency. Over here, I'm going to tell you that the frequency equals 40 hertz. I want you to find the period. Go ahead and pause it and give it a chance. Okay, what we find out here then is over here on the left, the frequency is 1 over 0.2 or 5 hertz. On the other side here, if I put 40 in for frequency, it becomes 1 over t. We've learned that the 40 and the t can just be interchanged, so the period becomes 1/40th, which is 0.025 seconds. So the period is 0.025 seconds. Pendulum swings back and forth in simple harmonic motion, a distance of 50 centimeters end to end. If it is going at 3.5 meters per second as it passes the center of the swing, what is its period? Well, the period is the time it takes to go to and fro of this pendulum. So we know that this pendulum, it said it goes from end to end, from here to here, is 50 centimeters. And then it's got to go back. So how far is it covering? It's covering 100 centimeters, or the distance is 1.0 meters. If it's going 3.5 meters per second, all right, we can find its period because period is just time. So we could say distance equals velocity times time. So in this problem here then, we have a distance of 1 meter. The velocity is 3.5. We can solve for t. We find out that t, or the period, just look a little better here, the period is 0.29 seconds. Well, what's its frequency? Again, just go back to your equation. 1 over 0.29, which means we're going to inverse it. And you get 3.45 hertz. Right. Hopefully that was pretty simple for you. One thing I want to introduce here to you before I let you go today is the period of a pendulum. There's a simple equation here, provided the angle is small. All right, so if we're talking about a pendulum here, the angle's got to be small. We've got this pendulum. So we're talking about theta here. This here has to be a small angle. You can't bring it all the way up here so that it's a right angle. That would be too big. So provided the angle down here is small, all right, our equation for the period can be calculated for any pendulum. We take the length of the string. This right here would be L. Actually, it goes all the way down to here. So this right here is L. G is gravity, we know that. So the only thing we'd have to measure is the distance from here to the bottom of the pendulum, and we can calculate the period of any pendulum from that. Hey, I hope this has been interesting for you. I'll see you on the flip side.